All right, hello everyone. Welcome to the next lecture, lecture number 14. The previous lecture was 13, so we skipped 14, and that lecture was because we had a midterm. Um, Anyhow, moving to lecture number 15 now. Again, in this chapter, we are applying Laplace transform applications on the circuit. In the previous chapter, we looked at how we can model a resistor into a Laplace transform, which essentially remains a resistor. The Ohm's law remains the same, and resistance comes out to be constant, right? And then we also looked at how to model a capacitor and an inductor with the initial energy stored. And then we came up with these two different models, a parallel and the series one, and we kind of discussed that how to pick which one to pick in which kind of applications. So in this lecture, we're going to kind of continue with the example problems. We did a bunch, at least like two or three of them in the last lecture, and we're going to do another like around like three of them in this lecture today as well. Um, okay, so let's get started. We again in the last lecture we did some RC, RLC, RL circuit problems in the S domain. The last problem that we did, because the first problem that we're going to do today is we're going to do an RLC circuit, and we're going to see something around superposition. We're going to apply superposition to the circuit in the S domain. So what do I mean by that is, so for example, here's the example problem, and this is kind of a continuation of the previous example. So let me kind of give you a quick recap of what was the last example that we did there. This is again the 13D example problem. In this example problem, we were given a time domain circuit, which was this one, where we had a inductor, capacitor, and resistor all connected in parallel with a current source, and it was a step response because our source came into the circuit at time t equal to 0. And we do had initial energy stored in the inductor and the capacitor as well. So the very first thing, we ended up writing down the initial conditions. Then we Laplace transformed the current 24 milliamperes. We also converted resistor and the capacitor and the inductor into their S domain models, and we ended up forming the circuit, right? Okay, and then we had resistance and inductive reactance, or we had impedances, right? We have impedance from the inductor and the capacitor as well, and the resistor resistance too. So we kind of combined all of them together to find the Z equivalent. And then we had three different current sources. One was this original current source that came after the switch enters, and the two other sources of energy, if you will, came when we modeled the resistor and capacitor and the inductor in the S domain, right? And their initial energies. So the two of these sources came, these current sources came due to the capacitor and the inductor modeling of the S domain. So we ended up finding an I equivalent, and at the end of the day, our objective was to find V of S, right? Again, this V of S, the final voltage, we ended up finding this final voltage in the Laplace domain, and again in the time domain over here as well, by looking at all of these three sources together. So today's example problem is starting from the S domain equivalent circuit, right? Again, this was a time domain equivalent circuit, and we ended up converting this into an S domain here, and our example problem is starting from this S domain circuit, right? So let's say this is a S domain circuit that you have. Okay, now, so let's see, this is the S domain circuit that you were working on from the previous example. So this example problem essentially talks about this concept that, in order to find this value V in the S domain and later in the time domain as well, right? One, of course, you can handle all the three sources. For example, all the three sources, including this source, and this source together, or you can handle them separately. So that, and then you can add them together by a superposition principle, which is essentially you are going to add them up. So let's get started, and we are gonna essentially, in this example problem, I'm gonna find this voltage V in the S domain by considering one source at a time, right? First, we're gonna consider this source, which is because of the capacitor, for example. Then we can consider the inductor source, and then we can consider the original current source that came into being into the circuit after the switching event. And then we're going to add three of them together to show that we are working with a superposition principle. Okay. Now, the very first thing to do would be I have to find the Z equivalent, right? Because I'm going to bring one of the current sources at a time, I have to find all the resistance and the impedance of the inductor and the capacitor are all connected in parallel, so I have to find Z equivalent. So I'm going to start with finding Z equivalent, and again, Z equivalent is 1 over R plus 1 over ZC plus 1 over ZL inverse, right? And Z equivalent is, again, you have 1 over 500 plus 1 over ZC. The capacitance one is this, 1 over 40 times 10 to the 6 S plus 1 over ZL. ZL is S over 40 inverse. Yeah, this is a, okay, yeah. And then again, we have evaluated this expression in the last example, so I'm just going to write this thing down. I can show you the expression as well, right? So this was the expression that we determined. So I'm going to use this expression here. Again, you can always solve this thing as well and find that expression. So the Z equivalent is going to come out to be 40 times 10 to the 6 S over S square plus 80,000 S plus 16 times 10 to the 8 ohms. Okay, so this is the Z equivalent. Okay, great. I got the Z equivalent. Now let's start to, before we apply the superposition, let's start to find the value of the V just by looking at one of the source, right? So the first one is, let's call it A, considering only capacitor initial energy. If I'm only going to consider the capacitor initial energy, again, this means that I have to bring in this source and I can take the rest of the two sources out. So my circuit will be, I can draw the equivalent circuit here. My circuit will be reduced to something like this, right? So this is your 500 ohms. This is S over 40 ohms. Sorry, this is this inductance, and this resistance is this resistance. This is this is the impedance. This is that ZL, the impedance of the inductor, right? And then this current source was 1.25 microvolts ampere second should be, yeah. And the capacitive impedance is 40 times 10 to the 6 over S. Right, so this should be ampere second ohms. Okay, great. So you ended up finding the equivalent circuit by only considering this source. Let me call the source A. Then I'm going to do B, and then finally we can do the C one. Okay, so we are doing an A1. One more thing is, let me call this voltage V dash, because this is just based on one of these current sources, not all three of them. So let me find this voltage. This V dash would be equals to, again, Z equivalent, which is going to remain the same because we are still considering the impedance of the inductance and the capacitance and also the resistance as well. So Z equivalent times the source, 1.25 into 10 to the minus 6. So if you were to solve that, and again your Z equivalent is this thing, multiply that by 1.25 into 10 to the 6, the answer is going to come out to be 50 S over S square plus 80,000 plus 16 into 10 to the 8 ohms. Okay, so this is good. So this is the V dash that came out to be. Now, I have seen this problem so many times in the past. We have solved many partial fractions like this, so I'm not going to follow all the steps, but I still want to show you the kind of the answers on how to solve that. Right, so for example, you can write V dash as 50S over S plus 40,000 square. So for example, if you were to solve this, s squared plus 80,000 plus 16, 80,000 s, sorry. Times 16 times 10 to the 8, right? It should come out to be s plus 40,000 whole square. Okay, and you can expand this by a over s plus 40,000 whole square plus b over s plus 40,000, right? And then you can, this is kind of a repeated roots that we have seen in the past. And you know how to solve them. We have done these examples. Go back to the previous chapter and do this thing. But you can easily find, from the looks of it, you can easily find the value of the a. The value of the a is going to come out to be 2 times 10 to the 6. And the value of the b should come out to be 50. So once you find these values, plug in these values over here. Okay, so let me plug in these values. So your v dash should come out to be, a over s plus 40,000. So a is minus 2 times 10 to the 6 over s plus 40,000 whole square plus b came out to be 50 s plus 40,000, right? And now I have to find the inverse Laplace transform. So for example, I can find v prime in the time domain equals Laplace inverse of capital V dash, right? And again, in order to find it, I can easily find it because I have seen these things in the past. The Laplace inverse of 50 of s plus 40,000 is 50 is a constant, e raised to power minus 40,000 t u of t, right? I should remember. And then minus 2 times 10 to the 6 over s plus 40,000 square. When we get a square in the time domain, it gets multiplied by a t, right? So you're going to get 2 times 10 to the 6 t e raised to power minus 40,000 t and the step function. So I can easily write this thing v dash in the time domain as 50 e raised to power minus 40,000 t minus 2 times 10 to the 6 t e raised to power minus 40,000 t, right? And this is u of t. Okay, awesome. So I ended up finding the component of this voltage value that was due to this energy source or this current source here. Now I'm going to repeat the whole thing again, and I'm going to find the value of the V, right? Let's call it V double prime, VB. And I'm going to do that for using this current source, which was 29 over S milliampere second. Okay, so B, considering inductor initial energy. So let's call this as, I am interested in finding V double prime. Okay, so if I'm gonna find V double prime, let's find the first, let's make an equivalent circuit of that, right? Again, in the equivalent circuit, all the three elements are gonna remain the same, right? So first we're gonna have a capacitor, then we're gonna have an inductor, then we're gonna have this current source, and then we're gonna have a resistor, and then we're gonna have a V double prime. Again, this was resistor, and the current was over here B, this is B, 29 over S milliamperes, 29 over S milliamp second. The inductor was S over 40 ohms, and the capacitor was 40 times 10 to the 6 over S ohms. Okay, great. So this is our new equivalent circuit that only considers this energy source, which practically came from the initial energy of the inductor when we modeled the inductor in the S domain. Okay. Again, simple. Your v double dash should be comes out to be z equivalent times this energy source, which is 29 over s into 10 to the minus 3, because it was in milliamps. And again, since you already know z equivalent, which is this one, so I'm going to take this and multiply this by 0.029 over s. So once I do that, right, my s will be cancelled out. So here I have an s in the numerator and I have an s over here in the denominator, so my s will be cancelled out. So the expression that I'm going to get after doing this thing would be a pretty simple expression, minus 1.16 times 10 to the raised power 6 over s squared plus 80,000 s plus 16 times 10 to the 8. Okay, and again this is v double dash. Okay, nice. Now this thing is interesting. I already know about this thing. This is s plus 40,000 whole square, as we have seen in the past. So I can rewrite this expression as minus 1.16 into 10 to the 6 over s plus 40,000 whole square. Nice. Okay, so this is my s domain expression for v double dash. Again, I need to convert that into the time domain. Interesting thing, I don't need to do the whole partial fractions things over here, because if you think I do not have an s in the numerator, and this s plus 40,000, I already know how to find the Laplace transform of this thing, inverse Laplace transform of this thing, right, from here. So I can do this v double dash in time domain, Laplace inverse v double dash in s domain, which is Laplace inverse minus 1.16 times 10 to the 6 over s plus 40,000 whole square. Okay, so once you do that, this v double dash in the time domain comes out to be minus 1.16 times 10 to the 6 times t e raised to power minus 40,000 t step function u of t. Okay, so this is the amount of the voltage across this resistance, right, that is due to this current source, this one. Now we are going to do that by looking at the last one, 24 over s milliamps second. And then we're going to combine the three. Okay, great. So we got this one as well. Now let's do the last one, which is C only considering independent current source. Okay, so if I'm only considering independent current source, and again I'm going to call it as V3 prime. Okay, so I should do it by remaking the circuit. Again, remaking the circuit, your resistor, your impedance of the capacitor, and impedance of the inductor will remain the same, will come in the circuit again. We are just picking one energy source at a time, so now I am picking my input source. Okay, so I'm gonna make the circuit. My input source came over here, capacitor, inductor, resistor, V triple dash, 500 ohms, S over 40 ohms, 40 times 10 to the 6 over S ohms, and this is 24 over S milliamp second. Okay, so once I find this, again the process is very simple. V3 prime should be Z equivalent times 24 over S 10 to the minus 3. Sorry, one thing, yeah. Okay. I already know the Z equivalent. Again, my Z equivalent was this one. It has an S in the numerator, and over here I have an s in the denominator. That will be cancelled out, so I'm gonna get a very similar expression to the B case, right? Okay, so once you're gonna solve this, you're gonna get the answer, which is essentially Z equivalent 0.024 over S. S will be cancelled out in the numerator of the Z equivalent, right? And the expression you're going to get is, again, a very simple expression, 0.96 times 10 to the 6 over S squared plus 80,000 S plus 16 into 10 to the 8. And again, this is a very simple expression as we have solved in the past. There is no S in the numerator, and the denominator comes out to be S plus 40,000 square. Again, we don't need to, this is a very simple expression. We can directly find the Laplace inverse transform, and we don't need to convert that into partial fractions or something like that. Right, so V triple dash time domain is Laplace inverse of 0.96 into 10 to the 6 over S plus 40,000 whole square should come out to be 0.96 10 to the 6 as is. S plus 40,000 is, since it is a square, so we're going to get a t and then an exponent minus 40,000 t, sorry about that, times the step function. Okay, great. So we ended up finding all the three values of this separately, right? For example, again, this value was just because of the input source. The V2 was just because of the inductor's initial energy, V double prime, and a V single prime was just because of the capacitor initial energy. And the whole idea was to show you that once we can also evaluate a circuit by just considering one of the sources and then kind of add them together to find the. So let's see. Now I'm going to apply superposition principle. Apply superposition principle, right? And the superposition principle simply states that this capital V should be equals to V prime plus V double prime plus V triple prime, right? In the S domain. And similarly, this in the time domain should be equals to V prime in the time domain plus V double prime in the time domain plus V triple prime in the time domain. So I can just find V of t should be equals to, I'm going to add all three of them. One of them is this, t times e raised to r minus 40,000 t, constant, t e raised to r minus 40,000 t with a constant. And the first one was t e raised to r minus 40,000 t with a constant, right? So I'm going to combine these three terms together and 50 e raised to r minus 40,000 t separate, right? Okay, so once I'm going to combine all of that, I'm going to get 50,000 e raised to power minus 40,000 t, and all the t e raised to power minus 40,000 t terms combined should give me 2.2 times 10 to the 6 t e raised to power minus 40,000 t and step function. And again, the units is volts. Don't forget the units. Sometimes I do. Okay, sounds good. So the whole thing that we did over here is we kind of solved the previous circuit problem. This was a previous circuit problem that we did in lecture number 13D, where we had a time domain circuit, and we did the whole analysis, converted that into S domain over here, and then we find the value of the Vs and inverse transformed if into the Vt. This is exactly the same expression that we got now, right? But now in this problem, we wanted to see the superposition principle application, the S domain, where and this is a kind of a very beautiful circuit to see this application, right? Because all the three, the resistance and the capacitive impedance and the inductive impedance will remain exactly the same. So you can just use as the Z equivalent again and again in all the three cases. And then you get to pick like one current source at a time and evaluate this value V, and at the end of the day you add all three of them up to get this expression, which is exactly the same expression that we got when we solved the whole circuit. Alright, so with that we're going to finish this part of our lecture, and we're going to do more example problems and understand more concepts in the S domain in the next part. Alright, thank you, have a good rest of the day, bye.